Okay, so let's see. Let's go over the homework. Quickly, you should have the solutions. See if there are any questions about this. Problem A is just a single pair of charges a distance d apart. The potential energy associated with that is simply that. And then this problem B has to do with this tetrahedron of four charges. The charges are on the corners of a tetrahedron, and you're given the coordinates in terms of a distance a for these four charges. Two of the charges are positive, two are negative, and you're to calculate the total potential energy of this arrangement. And so you look at the potential energy of each pair. Each pair has either a positive or a negative potential energy associated with whether they're the same type or the opposite. So there's two repulsive potentials, two positive potentials, and four negative ones. So the net here is going to be, let's see, negative q squared over root 2a is what you should get when you're all done in terms of a. Each distance here is going to be 2 root 2a. That is the length of each of the edges of the tetrahedron. And so you count those up. So they're all basically either plus or minus the same amount. You add 6 of them together. 4 are attractive, 2 are repulsive. That's the net. So what is the significance of this? The physical significance of this is that if I were to put, here's the center of the tetrahedron, if I were to put each one on a wire that connects to the center of the tetrahedron and put them all on at infinity at the ends of the wires, and let them now do what they're going to do, there's going to be and they all must move together. Okay, they can't move separately. They all have to move in together. So they're not only on a wire, but they're also constrained in such a way that they have the same distance from the center. Okay, it's kind of a constrained way of looking at it. But now if I let them all, they're going to be attracted, they're going to be pulling in, and the net is going to be the net work done by the electric force is going to be it's going to be negative, right? It's attractive. It's going to be positive work done by the electric force. So the potential energy is downhill, right? So the whole system would want to pull in. That's what the meaning of that negative total potential energy is. Or if I were to take them at that distance now and let go, they would want to, again, constraining them so that they all have the same distance from the origin, they're going to continue to pull inward. Okay, even though there's some repulsive interactions, the net is still attractive. Does that make sense? Okay, now we're getting into we discussed the current flow and the dimensionality of the current flow. Good morning, how you doing? And the all-important equation 220. And I want to talk a little bit about, good morning, how you doing? I want to talk a little bit about notation here. Okay, so let's talk about types of integrals. Okay, we've done a one-dimensional integral of some function along x. You could construct easily, and that's obtained by, as we said, taking in a one dimension, a section of x, the x-axis, breaking it into little pieces and summing them up. You could equally well do a two-dimensional integral, where now you're taking an area along the x and y axes like this, and you have little sections here of width dx and width dy, so there's a little increment of area, which is the product of dx and dy, so the area is dx dy. And now you're going to add something up over the area. So that's a two-dimensional version of it. Then the three-dimensional version would be to have gridding it up into volumes, x, y, and z, like this, and then you'd have a little volume inside of that, which is a product of three legs, dx, dy, dz, and then you're going to add up something over volume. So now we're not going to spend a lot of time going into how one could actually do these integrals but I want you're going to read the text, and he's going to use this notation just so you understand what he's getting at here. The integral over 1 dimension, 2 dimensions, 3 dimensions. So in the second case, you're integrating over an area. In the third case, you're integrating over a volume. And all you're doing is breaking it up into pieces and then adding it up. Okay? And so you could, in each one of these cases, you could integrate a function, for example, of x, or a function of x and y, or a function of x, y, and z. And then you're just multiplying the volume element or the area element by the value of the function, just add it up. Okay? That's all that is meant by that. So it's a very straightforward generalization of what we did in one dimension. Okay, now, you'll also encounter the idea of a closed surface. So in this case of doing a surface here, I've got a piece of surface. It's like a tile, a plaque in 2 dimensions. You're also going to encounter the idea of taking a complete closed surface. That would be, for example, a sphere or a cube. And then you're going to integrate over the area of a closed surface, and he's going to use this notation like this with that little circle around the integral. And that little circle implies that the surface encloses a volume. It's completely enclosed. Now, he's not, unfortunately, always strictly consistent in his notation. Sometimes you will see it with the circle around it like that. And sometimes you will see it without. Sometimes you'll just see it like this. Okay, equation 220, for example, equation 220 uses this latter notation. What he means there to be, he's more consistent later. This is what he means by it. It's a completely closed surface. That is, the volume is bounded by the surface. And this notation here, dV, means the boundary of a volume. And so that surface then is the boundary to a volume, and it completely encloses a volume. Surfaces like that would be, for example, a sphere or a cube or any shape. Now, we're only going to consider simply closed. That is, we're not going to have disconnected volumes. We're not going to have a little piece of volume over here that has some kind of closing surface and another little piece of volume over here that has another closing surface. That's too complicated for us right now. We're just going to have one connected volume enclosed by a simple surface. But it doesn't have to be a sphere or a cube. It can be any shape as long as it's connected. You can get so one part of the volume to another without going outside. Okay. All right. Now you're also going to encounter, we're not going to discuss it so much at this point, we're going to come back to it. You're also going to encounter this in your reading, that a path, which is the boundary to a surface. So if we take a surface that is not closed surface, a surface that like a square, it has a boundary to it, and the path around the boundary is the path that goes around the area. And so that's what's meant by this piece. ds here is the boundary to an area. And that would be, for example, if I have a circle here, the area is here, this is the S, and the boundary C is the piece that goes around it. Okay, so we're going to, that's going to be in your reading, and again, read through it, be aware of what he's talking about, but don't worry so much at the details of this part of the reading. We're going to come back in chapter 4 and consider that in more detail. We're going to focus on this first one for now. Integral around a surface that encloses a volume. Okay, and as I said, sometimes you'll see the notation, the proper form of that notation is this. Occasionally, as in equation 220, he does the shorthand like that. What he means by that integral with an S, this is what he means. It's a bounding surface. Okay. Okay, so now in equation 220, you see this J dot dA is equal to d volume by dt, where J is a volume current. It's taking volume and moving it around. And you can imagine an incompressible fluid, in which case now you're talking about moving the fluid. And J is the current, and you're moving the fluid. And then instead of on the volume on the right-hand side, you've got stuff. You know, it's the amount of stuff that you're moving. Could be mass, could be later charge, other things. Yes, Mr. Luca.
So why does the dA have the vector?
Good, very good. So that's here. Notice this dA. So now the magnitude of dA is a vector. And so it's the D in front indicates that it's a tiny piece. It's an infinitesimal piece. So its magnitude is the size of the area element. But what would be the direction? It's normal.
Increasing or decreasing?
Almost, yes, related to that. The direction of the area element now will give you so it's going to be perpendicular to the area. And notice that this is a bounding surface. So I could write this more carefully, more precisely as that. Okay, that points out here, that highlights the fact that what we're doing here is having a bounding surface. It's completely encloses a volume. Okay, now we can assign a direction to the area element. There's an inside and an outside. And so dA is going to point out by convention. So out. It points outward from a bounding volume. And so that way we can keep track of where there's flowing in and flowing out of this bounding volume. And that's the sense of the vector dA. Okay, so let's study that equation here for a moment. J dot dA, so if we have a bounding volume, so I have some kind of volume like this, and I've got a little area element here that's on the surface here, and I have a dA that's going to point straight out from the inside, points straight out, right? There's an inside and an outside, it's very clear. Okay, and now I have a current that could be flowing, for example, this way. Okay, so how much is flowing into the volume there is J dot dA. That's how much is flowing out, excuse me, how much is flowing out. So that's the net flux out. If J is positive, pointing out along the same direction the material is flowing out. So if we have, on the other hand, something over here, we have another area element coming out from this thing. And let's suppose that J at that point is into the volume. So now that will be negative. J dot dA will be negative. Here's negative if it's flowing in. Net flux out, net flux in. Okay, so now let's add up over the complete surface all of those contributions. I'm going to look at every little piece and figure out whether I'm getting J flowing in or flowing out, whether the volume is flowing in or flowing out, or the stuff is flowing in or flowing out. And I'm going to add it up over the entire surface. Now, I could have some flowing in somewhere and flowing out somewhere else. I might have a net zero. Or if I've got a net flow in or a net flow out, what's going to happen there is it's going to change what is inside. If I have a net flow in, I'm going to have more stuff inside now as a result. Or if I have flowing out, I'm going to have less stuff coming in as a result. Less stuff inside as a result. So, let's see here. Okay, so J dot dA, if oops, I need an, hang on a second. I'm going to need a negative sign, aren't I? No. Oh, that's the volume of water coming out. That's the volume of water coming out, right? That's what he means. It's the net volume of net volume coming out. So that's the rate at which stuff is coming out. Okay. That's why he has a positive sign there. So this is then stop. Okay. Now, based on that, then we get to Gauss's theorem. Gauss did a lot of stuff, and there's a lot of actually things that are called Gauss's theorem. There's also Gauss's law, which is a law of electrostatics. It's related to Gauss's theorem. So be careful here. Try to keep sorted out here. We're only going to consider one of Gauss's theorems and its relationship to Gauss's law. Okay, so Gauss's theorem, also known as the divergence theorem. Okay, so Gauss's theorem involves the divergence, and we need first to define the divergence. So we have the divergence of a vector. So this is the fundamental definition of the divergence. I'm going to take a small volume and enclose it with a surface, and I'm going to see how much of J is pointing out through the bounding volume. So it's the limit as the volume becomes small of the integral of J over that surface that bounds the volume. And I'm going to divide by that volume. That's the fundamental definition, the mathematical definition of the divergence of J. And that's what I want you to remember is the divergence of J. So I take a volume and shrink wrap it. And then I look at how much is coming out of that volume. And then I continue to shrink around that point. So the divergence is defined in the limit as that volume shrinks. So it's defined at one location. And that's the divergence. It's a lot like a derivative, because we did this as a derivative. It's similar to a derivative in that we took the location at 2 points and evaluated the function and then shrank that and divided by the interval. And then shrink that interval. It's a lot like that, except it's in 3 dimensions now. So we take an enclosing surface, and it doesn't matter what the shape of the surface is, as it turns out, as long as I have a well-defined, as long as I have a nice function that doesn't have peculiar characteristics. So most of the functions that we consider, most of the J's that we consider are going to be reasonable things. So it doesn't matter what shape that I actually use. Just like in the derivative, it doesn't matter whether you take the point at x and then go one step to one side, or I could step on the other side, or I could take the step half and half and then take the difference. As long as you take the difference and then shrink it, doesn't matter where you take that difference, you're going to get the same value of the derivative. In the same way, the shape of this volume doesn't matter. Okay, now he goes through this then, so you're going to read about this, and he goes through this on page 48. Now obviously I want you to read these very carefully, these pages. You only got about 4 or 5 pages. Read them very carefully because he lays the foundation. If you understand the divergence well, the rest of the semester will be much easier if you understand what's going on with the divergence. Okay, so now he works out the divergence in Cartesian form, but this is not the fundamental definition, right? The divergence in Cartesian form looks like this. Okay, where Jx, Jy, and Jz are the Cartesian components, and they are themselves functions of x, y, and z. So in other words, this vector field can be expressed in Cartesian form, which means that I can write down the components of the vector field. And each of the components depends on where you are, on the location, x, y, and z. I guess I should write this. Of course, this is some function of position, right? But I'm going to write it in Cartesian form. This is what I mean by Cartesian form of J. It's a vector, so I have x, y, and z components of the vector, and each one of the components depend on the x, y, and z coordinates of the point, of the location. And this is the Cartesian form of the divergence. It's a scalar. Why is it a scalar? not a vector.
It's dependent on position.
Yeah, but it doesn't have a direction associated with it. That's what we mean. So it's more than just dependent on position. It doesn't have a direction because you've bounded the volume, right? You've incorporated all directions in that, and you want to know what is the net flow in or out of this bounding volume. So there's no direction left. It's just a positive or negative. It's plus or minus. It's in or out, right? Net flow out, net flow in. There's no. You've accounted for all directions in this, added them all together in a sense. Okay, now another thing you will often see is the divergence may also be written this way, and this is this operator now called del or grad, and it is this operator that looks like this, and this was the same thing that we used for the gradient. So when we did the gradient, the grad of a function, grad f, we just applied this operator to f, and that was a vector. Well, in the divergence, we're going to take the dot product of that operator with J. It's a lot like that. You can see that then it looks like this. We have the operator on the left side. And then we're going to take the dot product with x, jx plus y, jy plus z, jz. And when you do the dot product, remember you expand that out, you're going to get 9 terms, but 6 of them are going to vanish because the unit vectors are perpendicular. So I'm only going to get 3 terms. And that's what you'll get up here, that line up there at the top. The divergence is the sum of those terms, right? It's just like, looks like the dot product between 2 vectors. But the grad is not a vector, it's a vector operator. It's not just a regular vector. Okay, but fundamentally the definition of the divergence is the one that you saw before there. That's the fundamental definition of the divergence right there. And he goes through and demonstrates in the Cartesian form as this. And very often when one is calculating things, you're going to calculate things in terms of the Cartesian coordinates, or you'll learn eventually polar and spherical and cylindrical other coordinate systems where the calculation is easier because of the symmetry of the function. It's just going to be easier to do it in a different coordinate system. But that all fundamentally goes back to this as the basic definition of the divergence. Okay, now let's see here. Okay, now let's suppose we look at this idea of having a surrounding volume. Oh, where's my pen? A surrounding volume. I guess I better start a new page here. A surrounding volume like this. And we want to account for all of the flow. Suppose that J is a mass flow. Okay, now this has got to be then the negative of the amount of mass, the negative time derivative of the mass inside. I should say inside here. Because the J gives you the mass flow, and the integral of J over the surface integral, gives you the amount of flow out. Well, if it's flowing out, that means there's got to be less inside. Okay. Okay, now let's go back to the Gauss's theorem then is written this way. This is Gauss's theorem. This is a mathematical theorem in the sense that it concerns quantity and the flow of quantity, the flow of volume. J represents here a volume flow, but it could also represent, by making this analogy that we've done to incompressible fluid, it could be a mass flow. J could be a flow of mass in an incompressible fluid, for example. but the fundamental definition is quantity. It's flowing of quantity. Okay, so what this says here, that this is like, in the one dimension, is like the fundamental theorem of calculus. The analog to this in the fundamental theorem of calculus was that, oops, I need to start this way. The difference in a function y, b, or I should use f b minus fa, that's the left-hand side. That's the amount of stuff flowing out on the ends, is equal to the integral of the derivative of f with respect to x. That's the one-dimensional version of it, which is the fundamental theorem of calculus. That's what we considered before. Gauss's theorem is like the three-dimensional version of that. You remember the fundamental theorem of calculus was you start here and you add up all of the differences over the intervals, and you'll add that to the original function, and you'll get to now where you are. In other words, if I walk from here to Greenville and I keep incorporating how much with each step, did I go higher or lower, closer to sea level or higher? If I just keep track of that, well, I went an inch higher or an inch higher, an inch higher, I'm going uphill. Now I'm going a series of steps an inch lower each step. I add up all of those increments, and I will get the net change in altitude between here and Greenville. That's the way of thinking of the fundamental theorem of calculus. Well, the three-dimensional version of that is Gauss's theorem now, where I'm including a bounding surface to a volume, and I want to know all of the stuff that flows out. Well, that will be related to the divergence. Okay. Now, combining those two things, Gauss's theorem and this relation gets me, if I have, for example, mass flow, this is the differential form of the same thing. There's two different forms here. There's the differential form, and then up at the top there is the, this is the integral form. They're both related to the same thing. The mass flows, it doesn't disappear. If the mass flows outward from some enclosing volume, then it's got to be less mass inside. And the differential form just says that locally. If there is a divergence in the field, that means there's less stuff at that point. It's going to be, with time, less stuff at that point. So you're going to look at the divergence of some fields in your homework, and just calculate the divergence of some simple vector fields, so you get a feel for what this looks like. Okay, now let me say here, if I have a field that looks like this, and I put a bounding surface around that point where it seems to be pointing outward, do I get a net flow outward? Yes. That means there has to be inside of there some non-zero divergence of the function. In other words, let's look at this. If I have some bounding volume like this, and this is greater than 0, like it is in this instance, and this is, according to Gauss's law, the divergence of J integrated over the volume has also got to be greater than 0. That means I've got to have, so divergence of J has to be non-zero inside. In fact, I have to have more positive than negative inside by Gauss's theorem. So you're going to look at some examples, vector flows. You remember you've plotted some of these vector fields that look kind of like that, like they're coming out, emerging from some point. You're going to draw an enclosing surface, calculate the flux, and just look at the divergence also in terms of the Cartesian form. Okay. Okay, now in terms of the mass density, This is called a conservation law, conservation of mass. It's a way of expressing conservation of mass. It says that water can flow around, but it's not going to disappear and it's not going to be generated anywhere. It's just going to flow from one place to another. We're not generating water, we're not destroying water. And we'll have a similar relationship having to do with charge. We're going to start looking at the charge flow. And the charge flow will be much the same as what we have here. We have the mass. We'll also have now a charge flow, which is a charge density times a velocity here. So here, this is the amount of charge. The dimensionality of this is charge per unit volume in time. And so the dimensionality of J is going to be charge per unit volume times the velocity. So it's a charge per unit area per time. Remember, we've talked about that before with mass flow, how much mass flows past a certain area in a given time. So it's a flux of charge. And the conservation of charge will look this, expressed in differential form, will look like this. This is the conservation of charge. Or expressed in the integral form, that if I keep track of all the charge flowing out past the bounding volume, that this will be the time derivative of the charge enclosed by that volume. So these both say the same thing, that a charge flows, neither generated nor destroyed. Now the trick here that's a little different than mass, the mass is always of one sign that we assign it. We always say it's positive, but we also have with charge two different types, which we assign to be positive and negative. And so in this current flow is the net current flow. They have opposite signs. So positive flow, positive charges flowing in to the right gives positive J, but negative charge flowing to the left also gives positive J. And that's different than mass, of course, because mass is always just of one type in the sense that we assign it a positive value. In the sense that it's, like the resistance to the impetus is always a positive resistance. It's not a negative resistance, not an opposite resistance. Okay, so you have to keep that in mind here, and that works. This does incorporate that. The ability to have two different signs. So see how compact it is. We can forget now that there's really two different kinds of charge. Now all we're talking about is just a net charge. And we incorporate them both into the current flow. So we don't know if we have a positive current flow, whether it's positive charge moving to the right or negative charge moving to the left. Both of those give a positive current flow. And we're going to stop keeping track of the difference between those positive and negatives and lump it all into one current flow. Just like we had a net charge, positive, and we have a net charge plus and some other, and the other charge, other type of charge, we call it negative. The net was just the arithmetic sum of the positive and the negative. We could have a neutral body which had just as much positive and negative charge present on it. We would say it has a net zero charge. Same thing with this current density. Okay. Okay, now you're also going to encounter the curl, but don't worry too much about the curl. I want you to read about it. Stokes' theorem and the curl. So you'll read about Stokes' theorem and the curl. So just as Gauss's theorem has to do with the divergence, so Stokes' theorem has to do with the curl. Don't worry too much about the curl, but I want to study here in kind of general terms, what is the difference between the divergence and the curl? Okay. So let's go back to this. We said there was a field like this take an example of a field like that. And it seems to be emanating from a point. Does it have a divergence? Well, it has to have a divergence somewhere in there, because I can draw a bounding volume and I get a net flow outward. So there has to be a divergence someplace inside. Divergence of this has to be greater than 0 somewhere inside. It's got to happen. Okay. Now look at what's happening in terms of the difference. The divergence tells you how a field is changing parallel to itself. So let's look at that. We have this vector here. And now I want to take the difference in that vector. Remember, the derivative of a vector is comparing the vector to itself somewhere else. And in this case, I'm going to make it the comparison to itself along its direction. So I'm going to compare the vector here to the vector here. That's what the divergence does. I'm going to compare how does the vector field change parallel to itself. And then you can maybe understand why it's written as the dot product of the gradient operator with the vector, right? Remember, the dot product gives you what do the two vectors have in common? Now, in this case, the gradient is not a vector itself, it's an operator, but it's saying that dot product gives you how does J change parallel to itself. The derivative is now parallel to J because I'm taking the dot product. So the divergence measures or gives how does J change parallel to itself. So what would be the contrast? What would be the opposite thing to do?
Perpendicular.
Right. How does J change perpendicular to itself? So I just gave you an example where J is emanating from a point where it looks like we can consider the change of J parallel to itself. Now let's consider the change of J perpendicular to itself. Can you give me an example of a vector field that changes perpendicular to itself? Any ideas? So if I have a J here, it's got some direction associated with it. Now I want it to change perpendicular to itself. I want there to be a change perpendicular to its direction.
Circular motion.
Ah, yeah, right. It'd be circulatory motion, right? I'll give you a simpler example. Circulatory motion is certainly included. Okay, J is changing perpendicular to itself, right? Here's the direction of change, but the direction of J is perpendicular to that.
Curl.
That's the curl. Okay. So we're going to get into more detail in the curl coming. You're going to read about it. I just want you to be aware at this stage the distinction between the divergence and the curl. We're going to study the curl more in Chapter 4. You'll see it introduced here. You'll see the Cartesian form of it. But it would be natural now to think about this for a minute. That's an example of a shear. Here's another one that you did, which was where it just circulates around like this, right? That was one that you drew pictures of. Oops, too big. Got too carried away there. Okay, that one has a clear kind of circulatory motion, vortex. The first one here on the left is a kind of pure shear. It's a kind of shear, but it would be like a flow that you might get in a fluid where the different parts of the fluid are traveling parallel to each other but with different speeds. So both of those will give a curl to the motion. Now, the curl, especially in the second case, you can see quite clearly defines a plane of motion. So in that case, you can see how the curl is going to be like a vector, like a cross product. And in fact, the curl will be written as the cross product of the gradient operator with the vector field. And there's now a direction associated with that because you have a plane of motion, and the perpendicular to that is going to be the direction of the curl. So we'll come back and study the curl. I don't want you to worry too much about the details of the curl and the divergence, but what I'm trying to give you here is a feel for the difference between them. They give you different kinds of information about the flow. In this case, you have flow that's changing parallel to itself. In this case, you have flow that's changing perpendicular to itself. And in one case, you have a divergence someplace inside in this region. In this case, you have a divergence, curl somewhere inside. This field does not diverge. If you calculate it, and you will calculate the divergence of this field, you'll see that there's no divergence. It doesn't diverge anywhere. If you can see this as fluid flow, you would say there is no buildup anywhere. It's not building up. There's no, which means that there's no divergence at any location. If I drew a surface around this and I look for the flow out from the surface, what do I get?
0.
I get 0 because at each point here, the fluid flow, the J, is perpendicular to the area. And so the divergence here of this thing, the divergence of what I've drawn here, without even giving you more details, you can see the divergence must be 0 because the net flow outward is 0. It's just circulating around. So the divergence of this is 0. And likewise, if I go back to the previous case over here, and I want to study the curl of this, not surprisingly, the curl of this will be 0 because there's no circulation associated with it. So what you're getting here is an idea that I have two different ways of describing the change of a fluid flow. That is, how fluid flow changes from one place to another is what I'm concerned with. Not just overall flow, but locally variations in the fluid flow. I have basically two different things that can happen. It can diverge or converge, or it can circulate. And that the divergence and the curl are ways of measuring those different kinds of possibilities and giving you a characterization of a fluid flow. So I can look at a flow field and determine whether it's locally it's diverging or curling, circulating or diverging. Okay, so the divergence is the first step in this. You're going to learn about the curl. As I said, read that. Don't get too caught up in the details of the curl yet. The curl is a little more complicated to calculate, but you can see the basic idea is not that complicated. Okay, so I'm going to give you a little preview. Do you have any questions about any of this? Yes, sir, Mr. Dowell.
So you're saying that divergence has to stem from a point?
Yes.
Like, so
well,
if you followed it backwards, it have to converge?
Not necessarily. You could have divergence that is spread out over a volume. That is, you could have a region where you have divergence all over that volume. Or it's possible to have divergence concentrated at a point. Yeah. So, and you'll see let me try to imagine the fluid example. The fluid example would be, suppose I have this and make a two-dimensional analog here. I have a two-dimensional surface. I have water flowing around on this thing, and I have just a very narrow stream of water flowing right here at this point, which reminds me of what I've had to do with at the house. You know, turn on the water upstairs, make sure the pipes don't freeze. So there's just this little stream of water flowing into the sink. And then the fluid would flow outward from that, but it's concentrated at a point. Well, let's suppose I had a bigger stream, and it's flowing down uniformly over a big area. Well, I still have fluid flowing outward from that, right? But the divergence now is going to be over a bigger area. So that shows you, and in fact I can get one from the other by making lots of fluid, spreading out the fluid flow. The very narrow stream, I could just spread it out. Okay, so it is possible to make a finite area or volume where the divergence is not 0. In this case, what you've seen right here, you can't really tell the difference. I haven't given you enough detail here. you can't tell from this really simple primitive sketch what the situation is. But you know that there's something putting fluid in there because it's coming out. So there's got to be a source in there somewhere. Okay, you just can't tell whether it's just a tiny little stream or a broader flow. And so, in fact, that's a very good point. We'll come back to study that. Other questions? Yes, sir.
So with divergence, like the value, it would be like a function,
Yes, that's right.
and so like at a certain point it would have a certain value.
Yeah, it's a scalar function. That's exactly right. Remember, an operator changes a function to a function. So the divergence changes a vector function to a scalar function. It's going to be a positive or a negative, which is telling you is it net flow out, net flow in, or zero means there's no net flow. Well, that's loud, isn't it? Okay. So the divergence being zero, there's no net flow in or out. Positive means it's flowing outward. Negative, but the divergence is defined shrink wrapping to a point. Okay. Okay. So now I'm going to give you a little preview where this is going. I mean, he's really trying to spend a lot of time walking you through very slowly through this so you understand conceptually where this all comes from, because the tendency, of course, in a lot of these introductions is simply give you the mathematical form, so you might be given the Cartesian form there, okay, that top line. Just give that to you and let you go. Right? He's not content to do that. He wants you to really take the time, understand what is going on with this. Okay, but you get to do all of the nice math too. It's interesting, very fun stuff, the vector calculus. Okay, now the connection to the physical. Let's go back then to, oops, I didn't want to put that there. Okay. Let's go back to the case where we have a charge, plus Q, in space, by itself, just a charged massive body is what we mean by a charge, right? It's a substance with charge on it, very small. Now, what does the electric field look like coming out from that? Certainly it diverges. And that electric field diminishes like 1 over the square of the distance. And I want to know what is the divergence of that electric field. Okay, now one easy way, let's look at the divergence around that point. Let's put a sphere around that point. And I want to look at the flux of the electric field coming out through that. I want to look at E dot dA. Okay, now remember the electric field is proportional to the charge, inversely proportional to the square of the distance, and points radially outward if the charge is positive. And what is dA? Well, dA points radially outward. It's a sphere, right? This is over the sphere. Radially outward. So the direction of dA is r hat. And then the magnitude is just a piece of a surface of a sphere, a piece of a sphere. So how does E compare, the direction of E compare to the direction of dA? It's the same. So this is just the magnitude of E times the magnitude of A. Okay, now how about the magnitude of E? How does that change over the surface, over the sphere? The sphere has radius r, and E depends on r. Every point on the sphere has the same r. So the magnitude of E is the same everywhere. So it's the same over the sphere, right? The magnitude of E does not change over that sphere. So the integral of E dot dA over the sphere, that is centered on the charge. E is a constant, so I can pull it out. The magnitude is a constant. I can pull it out. And then I just have, I need to calculate the area of the sphere. Well, what is the area of a sphere of radius r? 4 pi r squared. Oops. 4 pi r squared. You're remembering volume. And the magnitude of E is q over r squared. So this is 4 pi q. Now notice that it doesn't depend on the radius of the sphere. And that's because E is dropping off like the area of the sphere, right? And the area of the sphere, so you multiply the area of the sphere by something that's dropping off like 1 over the area of the sphere, and you get a constant. So this doesn't depend on the area, the radius of the sphere. Doesn't matter what size sphere I draw, I'm going to capture all the electric field coming out of the charge. That's what that says. All the electric field has to come out through the surface of the sphere. Doesn't matter how big the sphere is or how small. How big or how small. Okay, can you see a divergence about to come out here? We're about to use Gauss's theorem to get Gauss's law, which has to do with the electric field and the charge inside. Okay, so that's where we're going with this divergence. The divergence is going to be a property of that electric field that relates to the charge that causes it. And so we're going to have a relationship now between the electric field and the charge expressed in divergence. So we'll now have another form